All right, video three. Sorry, there's so many videos today. Right, simple harmonic oscillation. Uh, the position of a simple harmonic oscillator as a function of time is given to you in your AP equation sheet. It is the amplitude times the cosine of 2 pi, the frequency times the time. Which means it follows a sinusoidal relationship over time. The famous way of describing this is if you imagine like a reel of paper that is moving at a constant velocity, I guess it's going that way, and you had an oscillator with a pen on it going up and down, it would draw a perfect sine wave. And the same with a pendulum. Um, Cosine, sine, it's all the same thing, right? Sinusoidal means cosine or sine. Cosine is just sine phase shifted by pi over 2. Right, what we really want to know now is the period of spring oscillators, and then we'll talk about the period of a pendulum. So what I have here is I have the graph of this function. Basically, if we can just get rid of this phase shift, the phase shift is 0 right now, so just pretend that doesn't exist. We have a graph of the position of the oscillator as a function of time. Now, considering that the time it takes to get here, omega times the period is in essence 2 pi, right? Because when cosine is 2 pi, it's back to its start phase. So when this omega times the period equals 2 pi, we can actually rearrange this to solve for the period. So the period is going to be 2 pi over omega. And then that means the period is 2 pi over the square root of k over m. Remember, omega is the square root of k over m. And then that gives us the period is 2 pi over the square root of m over k. This, if you'd done enough trials, this is what the guys would have found in their spring experiment, that we found that it was directly proportional to the mass. So the more mass in a spring oscillator means the slower the period, the greater the period, so the more time between oscillations. And actually, the greater the spring constant, so the bigger the actual spring was, then the smaller. It's going to be a lot quicker the smaller the period. But the only thing you didn't find out with your data was that it's a square root relationship. But this is the reason why. Pause. All right, the last little bit to get the last equation we need. Pendulums. Same thing as a spring in the sense that it's an oscillator. It's just mathematically it's a little bit more complicated. When you look at it, the restoring force for a pendulum is gravity, which is actually going to be acting in that direction, mg sine theta. This is really oversimplified. Mathematically, it's kind of a little bit wobbly, but it will work for our intents and purposes. So the restoring force is mg sine theta. So I can say the restoring force, mass times acceleration, equals mg sine theta. The only thing is, the sine theta, if you look at it, we got L here, and on a microscopic level, we got kind of X working there. So sine theta actually equals X over L. Now I look at it, that's not technically correct, but we can basically come up with the equation A equals G over L times X. And again, we have a differential equation because A is D squared X over dt squared, and then we have basically the derivative equals the thing. So we have a differential equation. We're going to go through the same process again. We guess an answer. If it works, then we stick with it, and I'm going to guess this is my answer again. The only difference is I'm going to make omega equal the square root of the gravity divided by the length of the pendulum. Once you do that, it works just fine. Let me pause it in case I screw up. Wow, what on earth happened there? Let's go back. Let's go back. Alrighty, so let's just talk about the pendulum period. You guys did a great job in class of looking at the different variables. You found that length of the pendulum was the only thing that appreciably changed the period. The longer the pendulum, the greater the period. Mass really didn't have much of an effect, and the angle we can talk about in class has a bit of an effect, but not really. So really it's only length, but let's go ahead and prove that mathematically. We're going to start the same place where we're looking at the position as a function of time graph, which is a cosine function. X equals the amplitude times cosine omega t. And again, we know that the phase where it gets to one full period is 2 pi. So we're going to dance the same dance. We're going to say omega times the period equals 2 pi, which means the period equals 2 pi over omega. And that's 2 pi over, because we defined omega as the square root of gravity divided by L, we have 2 pi over the square root of g over L. So we're going to flip that, and we have this equation here, which is the equation on your AP question sheet. And this tells us that the period of a pendulum is 2 pi times the square root of the length. The longer the length, the greater the period, divided by gravity. That's a variable we couldn't test, and I didn't even mention it in class, because how can we test it unless we go to a different planet, or I decide to make artificial gravity by spinning you around real quickly? You can't really test it. One last thing I want to mention, then we're done for the day. Sorry it's taken so long. Okay, last little thing I just want to mention, just a recap of everything. We talked about frequency, we talked about period, and we derived a bunch of equations. I just want to make something clear. For any harmonic oscillator, the position as a function of time is given by this equation. A is the amplitude, the maximum amplitude, how far the pendulum is pulled back, how far the spring is displaced, times the cosine of 2 pi, times the frequency, times time. Now, maybe you'll have to find the frequency using omega, but let's not worry about that right now. But for the specific ones, for a spring, the period is 2 pi times the square root of the mass divided by the spring constant. And for the pendulum, it is 2 pi times the square root of the length divided by gravity. These make sense. With a spring, the greater the mass, the greater the period, the greater the spring constant, the smaller the period. And likewise with a pendulum, if you think about it intuitively, certainly after you have some experience, the greater the length, the greater the period. But if we had weaker gravity, stronger gravity, if you're on a real heavy planet, then it makes sense, it will be a lot more quicker. But for any harmonic oscillator, the period is given by this equation up there. And that is all I have for you today. Thank you very much for taking down your notes. Make sure you have these equations, and I will have a look at them tomorrow. Bye. Cheers.